This video is about L'Hopital's rule, which allows us to evaluate the limit of certain indeterminate forms. L'Hopital's rule says that if direct substitution yields infinity over infinity, or 0 over 0, then the limit of f over g is the same as the limit of f prime over g prime. Before you can use L'Hopital's rule, you have to show that you are approaching 0 over 0 or infinity over infinity. And you have to be careful about how you show it. You want to use two separate arrows, one for the numerator and one for the denominator. So x to the third power is approaching infinity as x approaches infinity, and the denominator is also approaching infinity. You have to describe it exactly like this. Don't say that the limit equals infinity over infinity, or even that the limit approaches infinity over infinity. Leave the numerator and denominator separate. Since we are approaching infinity over infinity, according to L'Hopital's rule, we can take the derivative of the numerator and the derivative of the denominator without changing the value of the limit. The derivative of x to the third power is 3x squared. When you take the derivative of e to the something, it doesn't change. You still get e to the something. However, because we have this function inside of a function, we have to do the chain rule and multiply by the derivative of this inner function. The derivative of x squared is 2x. Let's simplify this a little bit before we move on. The x in the denominator will cancel out one of the x's in the numerator, leaving behind 3x. I'm just going to put this 2 in the front, so we have 2e to the x squared. Let us once again consider what is happening to the numerator and the denominator as x approaches infinity. Well, 3x is still approaching infinity, and so is 2e to the x squared. As x gets bigger and bigger, both of these are approaching infinity. Since the fraction is still approaching infinity over infinity, we can do L'Hopital's rule again. Let's take the derivative of the numerator and denominator again and see what we get. The derivative of 3x is 3. The derivative of 2e to the x squared is still 2e to the x squared. But again, we have this inner function of x squared, so we have to do the chain rule and multiply by the derivative of that inner function, which is 2x. We can simplify this a tiny bit by multiplying 2 times 2, and we get the 4, and I move the x here in the front. But when we analyze again what's happening to this fraction as x approaches infinity, we notice that we have a constant in the numerator. So the numerator is just approaching 3, while the denominator is still approaching infinity. So if you have a constant in the numerator while the denominator is getting bigger and bigger and bigger, that means the value of the fraction is getting smaller and smaller and smaller, therefore approaching 0. So this limit is 0. Now, if you're thinking to yourself, wait a minute, didn't we learn how to solve problems like this back in Unit 1 using FEPL? Yes, you are correct. Back in Unit 1, we learned that factorials grow faster than exponentials, which grow faster than polynomials, which grow faster than logarithms as x approaches infinity. So we did not really need L'Hopital's rule in this case. X to the third power is a polynomial function, and e to the x squared is an exponential function. So according to FEPL, exponential functions grow faster than polynomial functions. So even though we are approaching infinity over infinity, we could just think to ourselves, the denominator is growing faster than the numerator. So if the denominator is getting bigger and bigger compared to the numerator, then the overall value of the fraction is getting smaller and smaller. In other words, the limit is 0. Problem number 30 is another problem that we could solve using techniques that we learned back in Unit 1. I'm going to go ahead and solve it using L'Hopital's rule first, and then I will remind you how we could solve it without L'Hopital's rule. Before I do anything though, I'm going to rewrite this slightly using fractional exponents. So this would be the same thing as x squared plus 1 to the 1/2 power. It is absolutely mandatory that you show this one little step for full credit. You must show that the numerator is approaching infinity and the denominator is also approaching infinity using these arrows. Since we are approaching infinity over infinity, we can go ahead and use L'Hopital's rule. Let's take the derivative of the numerator and the denominator. The derivative of x squared is 2x. I will have to do the chain rule in the denominator. So, according to the power rule, I'm going to move that 1/2 to the front. I will subtract 1 from the exponent, so I get negative 1/2. Inside, I still have the x squared plus 1, but I have to multiply by the derivative of the inner function. The derivative of this is 2x. Let's simplify. Notice that we have 2x in the numerator, and we also have 2x in the denominator. So those will definitely cancel each other out. Now we have 1 over 1/2 x squared plus 1 to the negative 1/2 power. However, when you divide by a fraction, you multiply by the reciprocal. So this 1/2 is going to end up as a 2. Also, because I have a negative exponent, I can bring this up to the numerator and make it a positive exponent. So I have x squared plus 1 to the positive 1/2 power. As x approaches infinity, this expression will simply approach infinity. In other words, the limit does not exist. Here's how I could have solved it using techniques that we learned back in Unit 1. We called it what matters most, and as x approaches infinity, the x squared will be growing rapidly while 1 is not changing at all. So the 1 will quickly become irrelevant, and the limit will be the same as the limit as x approaches infinity of x squared over the square root of x squared. Now, the square root of x squared is special. You used to believe that the square root of x squared was simply x, but we now know better. The square root of x squared is actually the absolute value of x. So if you did not know that, or if you forgot that, pull that back to the front of your brain. The square root of x squared is the absolute value of x. However, because x is approaching positive infinity, we already know this is a positive number, so the absolute value is not really doing anything. So we get this, but of course this simplifies down to the limit as x approaches infinity of x, and we can see that this is just going to approach infinity. So again, the limit does not exist. Number 32, before we can use L'Hopital's rule, we have to show that the numerator and the denominator will both be approaching infinity. We can see that the denominator will approach infinity as x approaches infinity. However, as x approaches infinity, sine x simply oscillates between -1 and +1. So we do not have infinity over infinity. We will not use L'Hopital's rule. We don't need L'Hopital's rule. The numerator stays small between -1 and +1. while the denominator gets bigger and bigger and bigger. So the overall value of the fraction gets smaller and smaller. In other words, the limit is equal to 0. Number 34. As x approaches infinity, natural log of x to the fourth power does approach infinity. And of course, x to the third power also approaches infinity. You must show this exactly like I did before you can use L'Hopital's rule. Because we are approaching infinity over infinity, we can go ahead and take the derivative of the numerator and the denominator without changing the limit. The derivative of natural log x is 1 over x. However, we don't have a simple x right here. We have x to the fourth power. So we have to do the chain rule and multiply by the derivative of the inner function, which would be 4x to the third power. The derivative of x to the third power is 3x squared. Let's simplify right here a little bit. We have the x squared and the x to the third power. The x squared will cancel out 2 of these x's, so we will be left with 4x in the numerator, and the denominator will just be 3. So we still have 1 over x to the fourth power as well. If I multiply 1 over x to the fourth power times 4x, which is like 4x over 1, I'm going to end up with 4x in the numerator and x to the fourth power in the denominator. And then I'm dividing all of that by 3, but we know that when you divide a fraction by something, it just ends up multiplying the denominator. So I'm just going to move this 3 up to the denominator. So now I have this, but I can cancel out this x with one of these x's. So that's going to leave me with x to the third power in the denominator. In this form, we can see that the numerator is a constant, so that's just going to stay 4 always. But as x approaches infinity, the denominator is approaching infinity. So if you have a constant in the numerator and the denominator is just getting bigger and bigger and bigger, the overall value of the fraction is getting smaller and smaller and smaller. So the limit is 0. Now you might have noticed that this is another problem that we could have solved using techniques that we learned back in Unit 1. We could have used FEPL. The numerator is logarithmic, while the denominator is polynomial. Logarithmic expressions grow much more slowly than polynomial expressions. So while the numerator is approaching infinity, as well as the denominator, we can see that according to FEPL, the numerator is a slower infinity, while the denominator is a faster growing infinity. So we could just look at it and think to ourselves, if the denominator is getting bigger and bigger compared to the numerator, then the overall absolute value of the fraction is getting smaller and smaller and smaller. In other words, the limit is 0. So we could have solved this limit intuitively. Number 36. As x approaches infinity, the numerator is approaching infinity. And of course, the denominator is also approaching infinity. You must show this exactly like I did before you can use L'Hopital's rule. So now we know that the limit will not change as we take the derivative of the numerator and the denominator. The derivative of e to the x power remains e to the x power. However, because we don't simply have e to the x power, we have to do the chain rule and multiply by the derivative of this inner function. So the derivative of x over 2. Remember, x over 2 is really the same thing as 1/2 x. So the derivative of this will just be 1/2. So that's where this extra 1/2 is coming from. The derivative of x is just going to be 1. Getting rid of the 1 and putting the 1/2 in the front, we have the limit as x approaches infinity of 1/2 e to the x over 2 power. And as x approaches infinity, this whole expression will approach infinity. In other words, the limit does not exist. And yes, we could have solved this using FEPL from Unit 1. In the numerator, we have an exponential expression, and in the denominator, we have a polynomial expression. So while the numerator is approaching infinity and the denominator is also approaching infinity, the exponential expression grows faster, and the polynomial expression grows slower. So if you have a faster growing numerator, then the overall value of the fraction is just getting bigger and bigger and bigger. In other words, the limit is approaching infinity, which means that the limit does not exist. For number 38, if we do direct substitution, the numerator becomes the natural log of 1, which is 0. In the denominator, we have the sine of pi, and the sine of pi is also 0. So, because we have 0 over 0, we can do L'Hopital's rule. So let's take the derivative of the numerator and the denominator and see what happens. The derivative of natural log x is 1 over x, and the derivative of sine is cosine. So I'm going to write cosine pi x. Because this is not just simply x, I have to do the chain rule and multiply by the derivative of the inner function. The derivative of pi x is pi, so I'm going to have this extra pi sitting here. Side lesson, remember that if you take a fraction and you divide by something, whatever you're dividing by just ends up in the denominator. So in this little example, I would end up with a over bc. I'm mentioning this now because I have this fraction 1 over x divided by all of this stuff, but everything I'm just dividing by is going to end up in the denominator next to the x. So I have this. Now direct substitution gives me 1 over pi, all right, this x is a 1, so I'm not going to write anything, cosine of pi, again this x is a 1, so I don't write it. And then the cosine of pi is negative 1. So that's just going to be pi times negative 1, which really just makes this negative 1 over pi. So that's the limit. And this is an example of a problem that we could not have solved using our techniques from Unit 1. So sometimes you really do need L'Hopital's rule. Ooh, number 40 has an arctangent in it. Interesting. Obviously, as x approaches 0, the numerator is approaching 0. But what about the denominator? If we do direct substitution, arctangent of 2x becomes arctangent of 2 times 0, which is arctangent of 0. So we just need to remember that this means the tangent of what is equal to 0. Right? This is what arctangent means. And we do have to keep in mind the restrictions. Arctangent is limited to the interval between negative pi over 2 and positive pi over 2. So we have to stick over here on the right side of the unit circle. So I ask you again, the tangent of what angle is equal to 0? Well, I submit to you that the little question mark would have to be 0 itself. So in other words, the tangent of 0 is equal to 0. And here's why. So at 0, we have the coordinates 1, 0. So the tangent of the angle 0, you know that tangent is going to be y over x. It's sine over cosine. So tangent would be 0 over 1, which is 0. So that's why the tangent of 0 is 0. So the arctangent of 0 is 0. I said all that to say that the denominator is also approaching 0. You must show this little step right here. Since we are approaching 0 over 0, that means we can use L'Hopital's rule. Let's go ahead and take the derivative of the numerator and the derivative of the denominator and see what happens. Hopefully you remember this fact that you should have memorized long ago. The derivative of arctangent is 1 over 1 plus x squared. So that's about to happen. The derivative of x is 1. So now I'm doing this. So I have 1 over 1 plus x squared. Instead of putting x, I'm going to put parentheses squared because we have 2x, not just x. So you know that when I have a function inside of a function like this, I have to do the chain rule and multiply by the derivative of this inner function. The derivative of 2x is 2, which normally I would just put off to the side, but I think I'll go ahead and put it in the numerator in this case. So, dink, I'm putting the 2 right here. That's my chain rule happening. I have a fraction. I'm dividing by a fraction. And when you divide by a fraction, you multiply by the reciprocal. So that's about to happen. So I'm just going to flip this upside down. So I will have 1 plus, I think I'll go ahead, no, I'll just leave it. So I have 2x squared over 2. So what's happening now? Let's reanalyze. If I do direct substitution, I'm going to get 0 right here. So the numerator will just be 1, while the denominator remains 2. So I can actually put an equal sign now. So I'm just doing direct substitution, and I'm getting 1/2. Actually, I think we should always show the direct substitution for the AP exam graders. So we would have this, and then 1/2. On number 44, if we try to do direct substitution, we run into trouble right away because the cotangent of 0 is undefined. Quick review, we know that cotangent is x over y, and at 0, the coordinates are 1, 0. So x over y would be 1 divided by 0, which is undefined. So we can't do direct substitution, but it looks like we can't do L'Hopital's rule either, because we really need some sort of a fraction. So we can get 0 over 0 or infinity over infinity. So we have no fraction. Or do we? We know that we can think of cotangent x as 1 over tangent x. So the original problem would be the same as this. But we could really just put this x to the 3rd power in the numerator at this point. So we have this now. As x approaches 0, the numerator is approaching 0, and the tangent of 0 is also 0. You must show this. Since we are approaching 0 over 0, we can use L'Hopital's rule. So let's take the derivative of the numerator and the derivative of the denominator and see what happens. The derivative of x to the 3rd power is 3x squared. The derivative of tangent is secant squared. As x approaches 0, the numerator is still approaching 0. But what about the denominator? Picture direct substitution. So what is secant squared 0? Well, secant is the reciprocal of cosine. So just real quick, cosine of 0, which is over here on the right-hand side, that's 1, 0, cosine's the x value. So this would be 1. And then secant is the reciprocal of that. The reciprocal of 1 is still 1. So secant of 0 is 1, and 1 squared is still 1. So the denominator is approaching 1. Since we're getting an actual value that is defined, I can use an actual equal sign. So the limit equals 0 over 1, which equals 0. By the way, at the beginning, when I dropped the cotangent down to the denominator and made it tangent so I could use L'Hopital's rule, I actually had a choice. I could have dropped the x to the third power down to the denominator and made it x to the negative 3 power. This wouldn't have actually solved the problem because when you do your direct substitution, the cotangent of 0 is still undefined. So this wouldn't have worked out, but I wanted to emphasize to you that you always have these two choices. Sometimes you're going to drop the first thing down to the denominator, but other times you will drop the second thing down. So it's not always obvious which one has to become the denominator. So you might have to just do a little bit of trial and error. If it doesn't work out the first way, flip it around and drop the other expression down instead and see what happens. Number 46, as I analyze this in my mind, I can see that, of course, x is approaching infinity. But then I have this other part, 1 over tangent x. As x approaches infinity, 1 over x is approaching 0. And then I have the tangent, maybe I'll just show this. So then I would have the tangent of 0, but the tangent of 0 is 0. So I end up with this sort of infinity times 0. This is meaningless. Don't think to yourself, oh, well, 0 times infinity is equal to 0. All right, that's a big mistake. That's not true. This is indeterminate. We have to do something else. And you can probably guess I'm going to do L'Hopital's rule. So I need to drop one of these expressions down to the denominator. Let's try just taking the easy way out and dropping x down and see what happens. So this would be the same thing as the limit as x approaches infinity of tangent 1 over x over x to the negative 1 power. So I just took this x and I dropped it down. Now, as x approaches infinity, the numerator is going to approach the tangent of 0 because 1 over x will approach 0, and then the tangent of 0 is equal to 0. So the numerator is approaching 0. And what about the denominator? So as x approaches infinity, x to the negative 1 power, I'm just going to do this off to the side, this is like having 1 over x. So as x approaches infinity, this is approaching 0. So for the AP graders, we must mention that the numerator is approaching 0 and the denominator is approaching 0 before we can go ahead and use L'Hopital's rule. So this should be the same as the limit as x approaches infinity of, and we will do the derivative of the numerator and the derivative of the denominator. We know that the derivative of tangent is secant squared. So I'm going to put secant squared, but since it's not just an x, it's 1 over x, then I'm going to put the 1 over x, but then I have to multiply by the derivative of 1 over x. Well, 1 over x equals x to the negative 1 power. If I take the derivative using the power rule, I get that negative x to the negative 2 power. So that's what's happening. So I have, I'm going to multiply by negative x to the negative 2 power. In the denominator, I'm doing that same thing. The derivative of x to the negative 1 power is negative x to the negative 2 power. Interesting. Well, since I have negative x to the negative 2 power in the numerator and the denominator, I can definitely cancel that out. So I end up with the limit as x approaches infinity of secant squared 1 over x. However, as x approaches infinity, 1 over x approaches 0. So this will equal secant squared of 0. And this is just 1, and that's going to be the answer. But real quick, this is 1 because secant is the reciprocal of cosine. So what's cosine of 0? We know that cosine of 0, which is right here at 1 comma 0, cosine of 0 is 1, which means that secant of 0 will be the reciprocal of 1, which is also 1, which means that secant squared will be 1 squared, which is 1.